Hi, good afternoon to all. This is the seventh week tutorial session for the NPTEL course Principles of Hydraulic Machines and System Design. My name is Ananthakrishnan. I'm a Ph.D. candidate from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. So in this week, we will be looking at a few multiple choice questions based on the previous week's lectures. Those are based on the radial equilibrium of axial pumps and series and parallel operation of pumps. We can move to the questions straight away. Read the question. Radial equilibrium of the axial flow pump is attained if four options are given. Force due to radial pressure gradient is equal to centrifugal force imparted by the pump impeller. The force due to radial pressure gradient is equal to the centripetal force imparted by the pump impeller. Force due to axial pressure gradient is equal to the centrifugal force imparted by the pressure by the pump impeller. Force due to the radial pressure gradient is equal to the Coriolis force imparted by the pump impeller. Am I audible? Was the question clear?
Audible. So option 1 is the correct answer.
Yeah, right. Yes. Yes, the right option is option 1. Radial equilibrium of the axial flow pump is obtained if the force due to radial pressure gradient is equal to the centrifugal force imparted by the pump impeller. So this is a right answer, and we will try to derive an equation that relates the radial pressure gradient and the centrifugal force imparted by the pump impeller to form a mathematical basis for the given statement. So in the case of radial equilibrium, before that we will try to draw a small diagram of axial pump operation. So in this one, consider this to be the axis z direction, and this will be the r direction, and theta direction will be perpendicular to the plane of the paper into the paper. So assume this pump to be rotating in clockwise direction. So in this particular analysis, we demarcate two separate points or two separate sections at the beginning and the end of a blade section. So consider this to be 1, 1, and here it is 2, 2. 1, 1 dash and 2, 2 dash. So what we can see is that before and after the blade section, there will not be any change in the streamline direction of fluid. So just inside the control volume we have drawn, there will be a change in the streamline, which indicates that in this direction, in the R direction, there will be a change in velocity within the control volume. But outside this control volume, there will not be any change. That will be a change will not be felt in R direction of the velocity. So this means that the radial equilibrium analysis is not satisfied within the control volume nearby the blade. That means the force due to radial pressure gradient is not equal to the centrifugal force imparted by the pump impeller within the control volume nearby the blades. But outside the control volume, there will be an equilibrium in the forces, because the radial the force due to the radial pressure gradient in one direction. So the streamlines will be parallel to each other. That means that the pressure gradient across this will be met by will be satisfied by the centrifugal force imparted by the pump impeller. As we go outwards, the pressure gradient increases. So the force due to the pressure gradient will be acting in this direction. The centrifugal force acting on the fluid imparted by the impeller will be acting in this direction. So they both cancel each other and the radial equilibrium will be met outside the control volume. Inside the control volume, it is not the case. So when the radial, so the question is regarding radial equilibrium of the axial flow pump. So we will try to derive a mathematical equation for the same. So what we can say is that in the case of radial equilibrium, there will not be, if there was a variation in radial equilibrium, these streamlines would not have been parallel to each other. Instead, they would have been they will not be a straight line, but rather they will be inclined a bit. They will be in much more like a staggered position, as you had seen in this control volume. So since it is not the case, we can assume that the radial velocity component in the case of radial equilibrium is equal to 0. Then we will try to equate a balance between, we will try to derive a balance between the centrifugal force as well as the radial pressure gradient based force. So centrifugal force is given by m v squared divided by r. Here v corresponds to the tangential component of the velocity, that is mc theta squared divided by r. Then this can be, this mass of fluid can be written as rho into if you assume a small control volume, the volume of the control volume can be represented as r d theta dz into dr and c theta squared divided by r. So this volume can be represented as, take a control volume of fluid. So this is center, and as it move outwards, its area increases. So take this control volume, whose which is at a distance of r from the center of the pump impeller. The dimension, the width dimension is represented in the radial direction is represented by dr, and the tangential component is represented by r d theta. This angle is d theta, so we can write this area, this length as r d theta, and along the axis, this is the z direction, so we can write this to be dz. So the control volume, the volume of the control volume is equal to the product of the three dimensions, that is dr multiplied by r d theta multiplied by dz. So that is represented by the volume. So we get the centrifugal force as rho into this particular term. If in the case of radial equilibrium, the centrifugal force will be balanced by the pressure gradient, the force due to the radial pressure gradient. So on the top of the control volume, a pressure P plus dP will be applied. At the bottom of the control volume, a pressure P will be applied. So the difference in pressure will be always compressive. The difference in pressure will be dP. So what we can say is that the force due to the pressure gradient is dP into the area of the control volume, the projected area of the control volume. So that projected area of the control volume will be coming as dP into on the projected area. So even if this is a triangle shape and the whole is a triangular prism, the projected area will be having an area of the top surface. So that will be equal to r d theta multiplied by dz. That's a rectangle. That's area is r d theta multiplied by dz. So dP into r d theta by dz will be the force due to pressure gradient. Pressure gradient in the radial direction. So in the case of radial equilibrium, what we can say is that for the case of radial equilibrium, we know that the force due to the radial pressure gradient equal to centrifugal force. So we substitute the values of this from the previous equations. So centrifugal force will be rho r d theta dz dr into c theta squared r. Rho r d theta dz dr into c theta squared divided by r. Force due to radial pressure gradient will be dP into r d theta dz. dP into r d theta dz. So we cancel these terms r d theta dz on both the sides. What we get is that 1 by rho into rho p by rho r is equal to c theta squared divided by r. So that will be giving the equation for the balance of centrifugal force and the radial pressure gradient in the case of radial equilibrium. So this particular term 1 by rho dou p by dou r is equal to c theta squared by r is valid for any value of c theta. This right hand side term, the left hand side term is always positive. So c theta can be negative or positive. this c theta squared by r term will be always positive. Since this is a square term, so the left hand side will be definitely positive. That means that dou p by dou r is positive. As we increase the dimension of the radius in the radial direction, the pressure increases. That means that P2 will be greater than P1. So outermost region for R2 greater than R1. So at an outermost radius R2, the pressure P2 will be greater than the pressure P1 at an inner radius. So this states that for a case of radial equilibrium, the outside pressure, the difference in pressure gradient from outside to inside balances the centrifugal force. So this is a mathematical formulation for the given question of radial equilibrium. But in this question, it was not asked. Just for the clarification, I have tried to derive this equation. So basic definition says that the pressure gradient force will be equal to the centrifugal force in the case of radial equilibrium. Is the question clear, or should I repeat something? Am I audible? Is the screen visible? Can you please tell me whether you can view the screen?
Yeah, visible, sir, visible.
Okay, thanks. So look into the second problem. It's a true or false question. Streamlines are perfectly parallel, very close to the blade of the axial flow pump. Is a statement true or false? It's a continuation from the first question. We have seen what happens within a control volume nearby the turbine blades, whether the streamlines will be perfectly parallel within that confined region. Is it true? If the statement given is true, then that means that it will be negating what we have told in the first question. So what is the answer for this problem?
It's false.
Yeah, right. It's a continuation. It's a false. So the streamlines would be following a zigzag pattern due to the change in the radial velocity component with nearby the turbine blades. But outside that, it will be outside the control volume, it will be following a truly parallel sets. It will follow truly parallel sets. The statement is false. So look into the third problem. It's a problem for the axial pumps. Axial pumps are used in applications where high head and high discharge is required. Only low discharge is required. Low head and high discharge is required. Only a high head is required. It's an application-based problem.
Option 3 is correct. Low head and high discharge.
Yeah. It can't deliver head because the development of the pressure head will be very less compared to that of the radial flow pumps, but it increases the discharge. It is capable enough of developing high discharge, but at a low head. So it is used for some mining applications or where a high quantity of water is required in a short period of time. Can move to the next problem. If the flow is free vortex flow and the pressure gradient is not changing along the radial direction, then the axial velocity component CZ varies linearly with respect to radius r. The axial velocity component CZ varies inversely proportional with respect to radius r. The axial velocity component CZ varies but does not vary with respect to radius r. None of the above.
Option 3, the axial velocity component does not vary with respect to radius r.
Yes, right. Okay, the answer to this problem is option C. The axial velocity component does not vary with respect to radius r. So we will try to derive the variation of the axial velocity component with respect to radius r. So before going to the derivation for the case of the free vortex flow, we will derive the mathematical equation for radial equilibrium for incompressible flow. So in the previous one of the previous questions, in the question number 1, we have derived this equation for the radial equilibrium. 1 by rho divided by dou p by dou r is equal to c theta squared divided by r. So this is a general equation which takes into account only the radial pressure gradient and the centrifugal force terms. So in reality, it's a 3-dimensional flow, and we need to take into account all the 3 components of the velocities. So what we try to do is that we will try to derive this equation for the radial equilibrium from the basic equation for the pressure and the stagnation pressures. So in the case of first question, we have written the equation dou p by dou r divided by 1 by rho is equal to c theta squared divided by r. This is the general equation for the radial equilibrium, where the pressure gradient force will be balancing the centrifugal force terms that takes into account only the tangential velocity component of the actual velocity. For the case of incompressible fluids like water, we can modify, we will get a modified equation based on the stagnation pressures. So we can write a stagnation pressure P0 is equal to the static pressure P. This is the static pressure term. Plus, we can modify this equation for the radial equilibrium based on the stagnation pressure. So that stagnation pressure component will be having the other velocity terms also, not just the tangential velocity component. So we can write the stagnation pressure P0 is equal to static pressure plus the dynamic pressure terms. So this is radial equilibrium, so we do not take the r component of the velocity, and represent this by 1, denote this by 2. We can differentiate equation number 2. Differentiate equation 2, we'll get dou p0 by dou r is equal to dou p by dou r plus half rho into dou by dou r of c theta squared plus cz squared. Now we will try to replace this static pressure term with the value of value which we have found from the radial equilibrium. So you can write dou p0 by dou r equal to rho into c theta squared divided by r plus half rho into dou by dou r of c theta squared plus cz squared. So it will be so we can write this equation as dou p0 by dou p0 by dou r p naught is the stagnation pressure term equal to c theta squared divided by r plus half into dou by dou r of c theta squared plus cz squared. So though in reality radial equilibrium, the pressure gradient force balances the centrifugal force, we can write a modified equation of that in terms of the stagnation pressure that is easily measurable. So that is a function of the centrifugal force term and a force term that will be taking into account the tangential velocity component as well as the axial velocity component. So this will be the modified equation of radial equilibrium for incompressible flow. Now, using this modified equation, we can determine whether the axial velocity component vary or vary not with respect to the radius r. In this particular question, it's been asked whether to find the four statements out of four statements, which is the right statement. So this question statement says the question statement has two given conditions. One is flow is free vortex flow, and the pressure gradient is not present in the radial direction. The pressure gradient is not changing along the radial direction. So that means that dou P by dou R is equal to 0. So that is a given question. That's a given part of this problem. The pressure gradient term is equal to 0. And also the flow is free vortex flow. So in the case of free vortex flow, we can write that RC theta equal to a constant. So that is the characteristic equation for a free vortex flow, taking into consideration the conservation of angular momentum. So what we can say is that the radius multiplied by the tangential velocity component is a constant for a free vortex flow. And the second condition is that pressure gradient is not changing along the flow. So we can say we can take the left hand side of the third equation, dou P0 by dou R is equal to 0. The variation of the pressure gradient along the stagnation pressure gradient in the radial direction will be equal to 0. So we can say left hand side is 0 and RC theta is a constant. So using these two conditions, we can try to simplify equation number 3. So for free vortex flow, RC theta equal to a constant, and we can denote it by K, and we can take the radial component of the stagnation pressure equal to 0, since it's mentioned in the question that's a constant term. So the equation number 3 reduces to d theta squared divided by r plus d by dr of c theta squared divided by 2 plus d by dr of c squared divided by 2 equal to equal to 0 by this particular term d c theta squared divided by r by plus d by dr into c theta squared by 2 can be simplified as c theta by r into d by dr of r c theta. So this term, when we differentiate r c theta with respect to r, we will be getting c theta plus r d c theta divided by dr. When we multiply it with the outside term, we will be getting this particular term will be c theta squared divided by r. The outside term will be c theta into d c theta divided by c theta into d c theta divided by dr. So this particular term can be represented as, if you multiply and divide it by 2 c theta, you can get it to be d c theta squared divided by dr divided by 2. So that is a simplification for the differential equation differentiation. So this particular term plus d by dr of c z squared divided by 2 is equal to 0. We can take, for the case of free vortex flow, we can take r c theta term is a constant, so we can write c theta by dr d by dr of k plus d by dr of cz squared divided by 2 equal to 0. Since this is a constant, so we'll get d by dr of cz squared divided by 2 equal to 0. That means that cz squared equal to a constant. That means that c is a constant and doesn't vary with respect to. That means that it doesn't vary with respect to r radius. So the equation, this equation proves that the axial velocity component cz will not vary with respect to r for the case of free vortex flow, and when the pressure gradient is not changing along the radial direction. So if you try to draw that, the schematic would come. It will be more like a uniform flow. For consider this section 1/1/2 and this section to be 2/2/2. At a single section, it will be having same velocity component in the radial direction. That means that it doesn't vary with respect to radius. This is the r direction, but it will vary with respect to all other components. This velocity term can vary with respect to the axial velocity term cz can vary with respect to z, but it will not vary in the r direction. So at one particular cross section, the value will remain a constant, as you could see at 1/1 dash and 2/2 dash. But the value at 1/1 dash will not be equal to 2/2 dash. So that is meant by the variation. That is meant by the constant nature of the axial velocity term in the radial direction. Is there any questions? Is there any questions? Should I clarify the explanation again? Is there any doubts?
Sir, yes, sir. How this? Can you please explain the c theta square by r plus d by dr c theta square by 2? How this becomes c theta by r d by dr r c theta? Can you explain that part alone?
Where? Which part? This or?
No, the c theta square by r. No, the next screen.
Yeah. This one, no?
Yeah. C theta square plus d by dr c theta square by 2. You are simplifying to c theta
Yeah,
by
yeah.
r. Yeah, that part. Yeah.
Okay, okay. So I can do that again. So we are trying to reduce this part into this form. This is basic differential equation. What we do is that c theta squared divided by r plus d by dr c theta squared divided by 2. That is given. So what we do is that we will represent everything in the form of d by dr and c theta terms. We do a reverse analysis in this particular case, and we try to attain this value from this analysis rather than going the other way around. So what we have right now in our hand, this is an easy way of doing. What we have right now in our hand is this particular term, c theta by r d by dr r c theta. So if we can prove this particular value after performing the differentiation will become the term in the bracket, then both are equivalent. So try doing the differentiation in this case. So it will be so it will come down to c theta. Try to differentiate the inner component. So it will be c theta by r into apply the differentiation of the product formula using the product formula. So d by dr of r c theta. So we differentiate the first term r, then it will become d c theta divided by dr. Then the second term again c theta by r into take r outside. So r c theta into d c theta divided by dr. So that will come down to c theta d c theta divided by r dr plus c theta d c theta divided by dr. So there are two particular terms. One is there is a small correction. I beg your pardon, there was a small mistake. So this is d by dr and c theta squared, because we are differentiating only r with respect to dr. So d c theta comes out, c theta comes outside. So it will come down to c theta squared by r plus c theta into d c theta divided by dr. So that can be written as c theta squared divided by r. The second term, when we multiply this by and divide by 2, what we can get is 2 c theta d c theta. So that is the differential of c theta squared. And because if you try to expand dc theta squared, that will be 2 c theta into dc theta. So that is this particular term. So what we get is c theta squared by r plus 2 plus dc theta squared divided by 2 dr, which is the initial value we had. So that means that this particular form, which is present in the bracket, reduces to this form. That is c theta by r into d by dr r c theta. Have I made it clear?
Yes, sir.
Can you move to the next problem? Is there any other doubts, or can
No,
we move
sir.
to the next? Yes.
No, sir. No.
look into the problem.
The first option is correct.
Yeah, right. So this is just a simple question that is based on the basic equations. In the case of free vortex flow, the distribution of angular velocity component c theta, whether it decreases with an increase in radius r, remains constant with change in radius r, develops parabolic profile both A and C. In the previous problem, we have seen that for the free vortex flow, the axial velocity component Cz does not vary with respect to r, but for the case of free vortex flow, free vortex flow or vortex free flow, we can write that the basic equation for the conservation of angular momentum says that R into C theta is a constant. That means that C theta equal to K by R. That is, it varies as radius increases, C theta decreases. So the profile would look like a hyperbola where the at a cross section 1, 1 dash. So the C theta component varies, decreases hyperbolically with increase in radius R. So profile of C theta will be hyperbola, decreasing hyperbola, where the magnitude of C theta decreases with respect to an increase in the radius R. So the option is 1. We can move to the next problem. Let's look into the problem and try to solve. We'll come back within a couple of minutes.
option 2 is the correct answer.
Right. So if the flow is forced vortex flow and the pressure gradient is not changing with respect to radius, then the axial velocity component CZ decreases with respect to radius. The radial velocity component increases with respect to radius. The angular component of velocity decreases with respect to radius, both A and B. So the option is option 2. The axial velocity component CZ decreases with respect to radius. How to derive it? We have to go to the basics of forced vortex flow and the equation for radial equilibrium. For forced vortex flow, so what we can say is that C theta divided by R is a constant. So that means that the velocity for the case of forced vortex, we can write that the tangential component of velocity is a product of radius and a constant. That constant can be angular velocity. So with respect to R, and if that angular velocity is constant, we can say is that what we can say is that C theta, that is tangential component of the velocity, will increase with respect to R. So this is first statement, and we can write it to be a constant K2 for the time being. And then in the given problem, it is mentioned that the pressure gradient is not changing with respect to radius. So we can write dou P0 by dou R is zero. So the basic equation that we have seen in for the radial equilibrium, this equation 3, 1 by rho dou P0 by dou R, this particular term will be 0. So only term remaining will be the right hand side term. And we try to substitute the value of C theta in terms of K2 and R in that particular equation. So this equation, after substituting equation 2, the reduced radial equilibrium equation would be after substituting equation 2 would be C theta squared divided by R plus substituting the case of vortex flow sub equation 1 in 3. Sub equation 1 in 3 will get C theta squared in terms of K into R. Before doing that, we can do a small bit of manipulation that we have seen in the previous one of the problems. So this will be c theta square divided by r. And this can be written as 1 by 2 into rho by dou r of c theta squared plus 1 by 2 into rho by dou r of cz squared equal to 0. So this whole term can be reduced to c theta by r into d by dr of r c theta. We have seen in the previous question how to simplify this equation into this form. So c theta by r, we have derived that specifically in the left hand side. So this is the simplification of the using the differential equation. So this particular two terms can be simplified into this form using this analysis. So the same we use here as well. We use this differential term as well as this particular term, and we simplify it into this particular form. Plus the second term 1 by 2 into d by dr of cz squared equal to 0. So we can denote this equation by 4. And now we apply the equation number, equation 1 in equation 4. So equation 1 is that c theta is equal to k into r, k2 into r. We substitute that in this particular equation. So equation 4 will be in all the c theta term can be written as k2 into r. So it will come down to k2 into d by dr into r squared k2 plus 1 by 2 into d by dr of cz squared equal to 0. Now we perform a bit of simplification. We can write this to be, since k2 is a constant, we can take it inside. So it will be by r2 squared, and this half also we can take inside the differential. So it will come down to d by dr of r squared k squared plus d by dr of cz squared by 2 is a constant. That means that d by dr of r squared k2 squared plus cz squared divided by 2 is a constant. That means that we can write cz squared by 2 is equal to cz squared plus by 2 plus r2 squared by k2 squared is a constant k3. So from this we can write cz is equal to root of 2 into k3 minus r2 squared k2 squared. So this variation of cz with respect to r2 squared will be in the form of this particular form. So cz will vary with respect to r negatively. So as r increases, the whole term decreases, and correspondingly cz also decreases. As cz decreases, as r2 increases, I beg your pardon, there is no 2 for substitute for r. This is r only. As r increases, cz decreases. So the variation of axial velocity component is that it decreases with respect to radius r, and it follows this particular equation. So option 2 is the right answer. the explanation clear, or should I clarify it better?
It's understood.
We can move to the next problem.
B is the correct answer. Option 1 and 2.
Right. Which of the following statements is or not correct regarding the types of pump? A radial flow pump is used to both moderate head and moderate to low discharge. Yes, that is right. An axial flow pump is used for high discharge and low head. Yes, that is also right. A mixed flow pump is used for moderate to extremely low discharge. That is wrong. A mixed flow pump will provide a better discharge at a better head. Though its discharge will be lower than that of axial flow pump, it will be higher than that of the radial flow pump. So the option B is the right answer. 1 and 2 are right. Now we can move to the next problem. Which of the following statements is correct regarding the series and parallel connection of the pump? Series pump connections are generally used to increase the discharge. Parallel pump connections is generally used to increase head. Series pump connections are generally used to decrease head. Parallel pump connection is generally used to increase discharge.
Option D.
Option
Parallel pump connection. A parallel pump connection is generally used to increase discharge.
right. So we use a series pump connection to increase the head, keeping the discharge to be almost a constant. And conversely, we use a parallel pump connection to increase the discharge, keeping the head almost a constant. So that can be explained in terms of the system characteristics. The case of a system series. We try to analyze the system characteristics versus pump characteristics for a series and parallel connection. That will make this analysis a bit more easier to understand. So this is the overall head and overall Q. And suppose this was the initial first pump set, characteristic curve. Corresponding system characteristic curve was this. So this was the operating point for the initial analysis. When we put a multiple pumps in series, this head curve will get accumulated over one over the another. Correspondingly, the new Correspondingly, the new headline would be this. Accumulating these headlines one over the another, keeping a discharge constant. So for a small increase in the Q, there can be a sufficient increase in the head. So this Q we assume to be almost a constant. The increase is marginal, but correspondingly the head increases by a significantly high amount. But another reason that, another feature that we could observe during the experiment is that increasing the number of pumps in series that requires a huge number of fittings additionally, and that reduces the discharge. And in reality, this new headline, the overall headline, come down drastically, and like this. That was a mistake. The new, when we increase the number of fittings, the system characteristic actually varies. The system characteristic might vary like this. In that particular case, we will achieve a higher head by accumulating one, by including a lot of pumps in the same system at the almost the same discharge. So this will be the new analysis for a series of pumps compared to a single pump which was used alone to meet the needs. The system characteristic itself will change based on the fittings as well as bends. So many things which will come into picture because of the addition of new sequence of pumps, addition of a few pumps in series. So this will be the new headline, and this will be the new system line, and this will be the new operating point. It will be at a higher head at almost the same distance. So a series of pumps will increase the head at almost a constant distance. So the options for series pump connections are wrong. In this analysis, it is used to increase the head at almost a constant discharge. And the other option are for the parallel pump connections. So whether it is used to increase head or increase discharge. Parallel flow pumps are used to increase the discharge, keeping the head almost a constant. So in the case of a parallel flow connection, the whole analysis is slightly different. So this was the initial headline and corresponding system curve was this one. So this is the operating point. So with coupling of more number of pumps in parallel, it increases the discharge, keeping a head almost a constant. So the new headlights of accumulating more pumps one over the another in parallel will be following this trend. And finally, the flow follows a new characteristic line of this particular poet. correspondingly, what we can see is that the discharge increases. Correspondingly, what we can see is that discharge increases significantly for a small increase in the head. So this is a discharge increase corresponding to a small increase in the head for the parallel connection. So the answer to this problem is that parallel pump connections are used to increase the discharge. So the option D is the right answer. This is for single pump. This is for multiple pumps in series. Similarly, this is for single pump. This is for multiple pumps in parallel. This is system line, system characteristic. This is pump characteristic. Similarly, this is pump characteristic. And these are system characteristic lines. Is there any doubts in this problem?
No, sir.
Look into the problem. The vertical line that passes through the best efficiency point and intersects HQ curve at a point is called break-even point, operating point, design point, and system resistance point.
It's design point.
Yes, right. So you try to draw the HQ line for a static head. This will be the system characteristic line, and corresponding the design curve, design point will be corresponding pump characteristic will be this one. So meeting of these 2 points is called the operating point, the system characteristic as well as the pump characteristic line. This is the operating point, and this is the design point, the intersecting point of the line that we draw from the best efficiency point, where it meets the HQ curve of the pump. That is called the design point. Yes. So the answer to this problem is it's design point. So this is the explanation, and there is another variation of power versus Q. The power actually increases with respect to the discharge or produced by the pump, power developed by the pump. That is that will vary linearly with the Q. As we could see that power equation for the head, equation for the power will be rho g into QH. So power varies almost a linear term with respect to the discharge. So these are the 3 main characteristics, the variations of the parameters. That is, H varies, the head variation with respect to discharge, efficiency variation with respect to discharge, and the power variation with respect to discharge. So the operating point is the intersection point between the system and pump characteristic, and the best efficiency point is the peak point, or where the efficiency reaches the maximum in the efficiency versus discharge curve, and dropping a line from the best efficiency point to the discharge, the point where it meets the SQ curve, that particular head will be corresponding that particular head corresponding to the discharge at which we get the maximum efficiency, that is called as design point. So this answer to this problem is a design point. Look into the 10th problem.
So option 1.
Right. If the pumps are connected in parallel, the head remains the same and the discharge increases. So the answer is Q equal to Q1 plus Q2 and H is equal to H1 plus H2. H is equal to H1 equal to H2.
You have to use the affinity laws, sir.
Yes, we have to use affinity laws, but there is a small correction. Those portions are not from the portions which have been taught in the previous week. So I'll change the problem. I'll give a new problem. That requires the dimensionless parameters that we have to obtain using the Buckingham pi principles. So that is not taught in this week's lecture. So I'll give another problem which uses affinity laws. Is my screen visible?
Yeah, visible.
Yeah, just try to do this problem. This uses affinity laws. You need not calculate anything related to the specific speed because that was not taught in this week's lecture, but try to do the other sections of the problem. So for this problem, just ignore this part. This is not required. Centrifugal pump rotates at 1800 RPM. That is a given condition. You can take it as N1 and delivers 0.4 meter cube per second, that is Q1 discharge at a head of 16 meters. We have to calculate the power input. We have to calculate P1. Assume the overall efficiency of the pump as 0.7. If this pump were to operate at 900 RPM, so this is N2 condition, what would be the head discharge and power required for homologous or identical conditions? Assume the overall efficiency is unchanged at the new RPM. So we have to calculate Q2, H2, and P2, and that uses the affinity laws. This particular problem, we can calculate the power. Input power is equal to the ideal head developed divided by I beg your pardon, the actual head developed divided by the overall efficiency. So that will be rho g q h divided by efficiency overall. So that will be 1000 into 9.81 into 0.4 multiplied by 16 divided by efficiency is 0.7. We'll get the power input rho 1 as P1, Q1. So this one Q1 and H1 and P1 power input P1 is equal to 89.69 kilowatt. So we have all the basic parameters at the first condition to determine the values of power head and discharge at the second speed condition. That is represented by subscript 2. So we use affinity laws to determine the values of this discharge at this discharge head and power at the new conditions. So we know that the affinity law says Q is directly proportional to the speed, head is directly proportional to the square of the speed, and power is directly proportional to the cube of the speed. So from this one, we can calculate the Q2, H2, and N2 values. Q2 will be equal to N2 by N1 into Q1. Similarly, H2 will be equal to N2 by N1, the whole squared into H1. Similarly, P2 will be equal to N2 by N1, the whole cube into P1. So from this one, you can calculate the values of Q2, H2, and P2 respectively. How much is the value coming at?
Q2 is 0.2.
Yeah, right.
Q2 is 0.2.
Yes.
H2 is 4 meters.
Yes.
So P2 is 11.21 kilowatts.
Yeah, right. So it's basic substitution. N2 is 900. So 900 divided by 1,800 into 0.4, it will be coming around 0.2 meter cube per second. And similarly, this is 900 divided by 1,800 divided by square into 16, that will be coming around 4 meters. And for this one, it will be 900 divided by 1,800 whole cube multiplied by 89.69. So it is 11.21 kilowatt. And that completes this problem. But there was one particular section to this problem that we didn't attempt this time around, that is calculating the specific speed. The specific speed for a hydraulic machine or a pump is given by the formula in root q divided by h raised to 3 by 4. So the specific speed is a dimensionless quantity for the speed that takes it into account the speed at which it runs and the discharge and the head. So this particular quantity remains a constant for geometrically similar pumps. So we can write n is equal to, in this particular problem, 1,800 RPM, and discharge n we have to substitute in revolution per minute. Discharge in terms of meter cube per second, and head in terms of meter, we will be getting a quantity, a dimensional quantity that using the same values of same dimensions of the speed, discharge, and head, we will be getting a constant for all the kind of pumps that we use. So in that particular case, Q we can write it as 0.4, and H we can write it as 16. So the specific speed will be coming around 142.3. Is a question clear? Are there any doubts?
No, sir, no.
Any clarification required on the topics which we have discussed for today?
Sir, pardon?
Is there any clarifications required for the topics which we have discussed today?
We are happy.
That concludes the questions for this session. So we had basically discussed a few problems on the radial equilibrium of axial pumps, series and parallel operations of pump, and solved a numerical problem based on the affinity laws. So in the next week, we will discuss a few topics, few questions basically based on the next week lectures, and that will be the continuation of the pumping system design of parallel pumping systems, and a few more multiple choice and numerical questions. And we'll meet next Saturday. Till that time, bye.
Thank you.